So today we'll discuss about futuristic interplanetary missions, the aspects of communication and navigation for the futuristic missions globally, as well as the planning of ISRO, in short. Uh, so coming to the next slide. So we'll start with the basic of communication anyway. The way it has started, mostly we are all familiar with this. That it has started with sending and receiving information. Mostly this was oral information conveyed through speech. Then subsequently we entered into telecommunication, where the signal, basically the speech or information, was transformed into a form of signals. First, we started with electrical signal, where the medium was wired, basically wired medium. From there, we have moved into wireless medium. So when we say wireless medium, it is basically, this is also kind of electrical signal only, but it's electromagnetic signal. As you all know that light is also electromagnetic signal. Similarly, these signals, the radio frequency signals, these are also electromagnetic signal. So this is the, you can see now how this wireless communication work. You might be familiar with your mobile communication. Everywhere we are using wireless communication nowadays. So basically, it works on the principle of line of sight. Most of the communication, major part, it takes place through line of sight. However, there are some ways where it is slightly deviate from the line of sight also, in a much larger scale due to some specific issues of refraction, and these are utilized in non-line of sight communication, NLOS communication it is called. Anyway, so when you are connecting users or the transmitter and receiver, which are widely separated, maybe other part of the world, there we have used this RF communication through satellite, where the satellite work as a relay. So as you can receive the signal 1,000 kilometers. Why 36,000? Because from the surface of the Earth, it remains stationary. It appears to be stationary on a particular place on the surface of the Earth. So the signal travels this wide distance of 36,000 kilometers, this large distance, goes to the satellite and then come back to the receiver, and vice versa. It can be a two-way communication also. The communication, majorly we are differentiating into two parts. One is a single, means one-way communication, and the other one is two-way communication. Like this TV communication, the television, DTH television, if you see, there it is a one-way communication. When we only receive the signal, as a user, you cannot transmit anything back to the service provider. So that is called one-way service. And mostly all one-to-one communications are two-way service. That means we are talking as well as we can listen also. So we can listen and talk. This is called two-way communication. Now, the major part of this communication system, that means the transmitter and the receiver, it all starts with the antenna. The antenna system is basically, it works as a, you might have seen the headlights of the car. If you put simply the small bulb and remove the reflector from the headlight, light will radiate, it will get radiated in all the directions, but you will not get a good intensity in one direction. So by putting the reflector in the headlight or in a torch light, what we do, we basically we direct the signal in a specific direction, the light waves, so that its intensity increases in a specific direction. So antenna also serves the same purpose. It directs all the energy, electromagnetic energy, into one, instead of getting it spreaded all over 360-degree things, where it directs it in a particular specific direction of the user, of the receiver, and vice versa from the receiving side. It collects the signal over a wide area, that is called aperture area of the antenna, and use the overall signal to get the transmitted signal back. So this is how the antenna is very, very important, both from the transmitter and receiving end. And the propagation medium, of course, in this case for electromagnetic signal, it may be vacuum also, or in the terrestrial communication, anyway, it goes through the atmosphere. So it doesn't depend, basically, the propagation doesn't depend on the medium, but it gets affected. If it is atmosphere, it gets affected to some extent because of maybe because of rain or any other weather condition. You might have seen that the DTH signal, it often goes off when there is heavy rain. So the propagation medium works there. It attenuates the signal. And by nature of the transmission of the signal, as I said, the reflector, it directs the energy, but still, if you see at a very large distance, say 36,000 kilometers, still the energy will get spreaded over a wide region. So when it's getting spreaded, it is basically its intensity is again getting reduced at a particular point. So if you see the receiving antenna, in that specific direction, a very small part of the energy is getting transmitted. So the remaining part is getting lost. So this is also a kind of attenuation, or we call it a spreading loss. And what is the minimum amount of signal that is required? Because when you put the receiver itself will have its own noise, because it's an electronic system, so electronic noise will be there due to motion of electrons. Then when it is looking towards free space or any other direction, from there some radiation will, unwanted radiation may come, and that will create a noise floor. So we measure the signal and noise in a spectrum analyzer. So we see the spectrum, the strength of the signal. But if the noise is very high or the signal level is very low, then it may get submerged into the noise. So the ratio of signal to the noise power ratio, that is very, very important. We call it SNR, or signal to noise ratio. So we may have to keep sufficient signal to noise ratio at the receiving end. That means our transmitted power should be sufficiently high, or maybe antenna should be large enough at the transmitting end and the receiving end also, so that we get a good amount of SNR, signal to noise ratio. Just remember this term; these are very, very useful for any type of communication. So usually for a large scale communication, we try to keep a very large reflector antenna so that we get a good communication link. So examples like our home Wi-Fi versus cellular rooftop antennas, the different types of antennas are used. So the issues with the signal transmission, particularly for deep space and when the signal is going far away, is the dynamics and orientation of the transmitter and receivers. Two important parts are time delay and latency. We'll come to the detail of these things. And the interference, that is the signal of other transmitters which may enter into the system, and the synchronization and coordination with the of the receiver with the transmitter system. So these are important aspects of any communication system. Next slide. Now coming to deep space, what is deep space? Because as I've told, that communication satellite may be at a geostationary orbit, that is at 36,000 kilometers. But that is not defined as a deep space. ITU has the International Telecommunication Union, who controls all this communication globally, and all even into the deep space also. That is called International Telecommunication Union. It is a global agency. So they have defined the deep space as a region which is beyond 2 million kilometers from the Earth. 2 million kilometers. Just remember the value, how large it is and how far it is. That is called deep space. Moon, as I know, 450,000 kilometers is largely in that range only. Distance of the moon from the surface of the Earth. Next. So how far we have gone so far? If you see, the two satellites, Voyager 1 and Voyager 2. This was launched in 77. Both the satellites were launched by NASA in 77. And they are right now, they're 167 astronomical units. AU it is called. AU means, 1 AU means the distance from Sun to Earth. So that distance is called 1 AU. So like that, 167 AU distance away, the Voyager 1, and the Voyager 2 is almost 140 AU away. And their velocity at present is around 17 kilometers and 15.4 kilometers per second. That means per second they can travel, the signal can travel at this rate. And one way light time, if you see, that means the time it takes from for the signal from the transmitting end to the receiving end at the Voyager is almost 24 hours, 23 hours, 9 minutes, and 19 hours, 23 minutes respectively. So these are far away. So like that, all the deep space probes are supposed to work over this large distance. Next. So if you see the brief history of deep space communication, like in 1957, we had USSR, the first satellite launched by USSR, that is Sputnik. Then in 58, we have NASA program. Like that, we know how it has progressed. Human has gone into the space. 1961, the Yuri Gagarin was in space from USSR. And then we have the lunar mission, Apollo missions. And recently, in 2020, first human mission, of course, beyond 2020. In future, we'll have a human mission to Mars also. And we already have international space stations. People are already going there, residing there and coming back. You might have heard about all these things. But so with all these probes and space stations, we have a very good connectivity, communication connectivity. Next. Okay, one more point. You can see that how does the Earth look like from the Voyager? It's a pale blue dot. So it's just a dot. You can see how this is the Earth actually as seen by Voyager. So you can can imagine about the distance where they are, where Voyager is located right now. So in an Earth to Moon typical, that is the first thing we can imagine in a deep space link, that between the Earth and the Moon. So there, the typical links, if we consider, is one major part is Earth-Moon link, that is the longest one, where the antennas located on the surface of the Earth may be communicating with the data relay orbiter or maybe data relay satellite surrounding the Moon. Then we have lander or rover on the surface of the Moon, and these are also connected with the orbiter. And there are maybe astronauts who are on the Moon, so they have connectivity with the lander or the rover. This is called surface link. And in some cases, even the lander can have a very weak link with the space also directly. But that is, of course, that will be very, very weak link. It's very, very probable that that link will not work. So it is better to get connected with the relay satellite, and the relay satellite will connect with the Earth. So that is the usual link. And sometimes there are other types of links also, like cross links. When we have two relaying satellites, then between them we may have cross links, proximity link, the link between the relay satellite and its service user, and of course surface to surface links in case of astronauts and other landed assets. So these are the types of links which are normally associated with the lunar communication. Next. So today, if you see the communication, it's whether it is Moon or Mars, it's basically it is controlled by a network which is called Deep Space Network, DSN. Is a NASA originated program and NASA control program, where they have three huge antennas 34 meter or 74 meter kind of diameter. And at 3 places over the world, they are having, and you will come to that, is a huge antenna system, 3 antennas. And with that, we get a good coverage in the free space, in the deep space. So this is the network, whatever we are having today. But in future, what will happen? Mostly it will be type of interplanetary internet kind of connectivity, where each planet will have its own network, like we have internet system on the Earth. So like that, there may be separate connectivities links in the maybe on the moon, or Mars, or any other planet. Then they may be connected together with the network, which is there shown in the red lines, and they may have connectivity with other things also, other planets or any deep space objects. Next. So if you move from communication, from this traditional deep space network, come to the next slide. If you see the traditional requirement, this GSN, whatever I mentioned earlier, this operates mostly in 2 frequency bands, S and K. These are all radio frequencies, S and K band they work. And there are 2 types of link. So one type of link is used for commanding. Suppose you have a space probe somewhere on the surface of the moon. So you may have to command it in what it is supposed to do there for that, to initiate those actions. So, but those links are very low volume data links, we can say. But they have to be of very good quality. They should not fail. So it is a low data rate, but very, very reliable links. For that is called the command link. That is from Earth to the space probe. And on the other hand, we have the space probe to Earth link, which is called the image telemetry, where the data volume may be quite high compared to the other side. And the quality may be moderate. Okay, if some part is lost, that is also acceptable. The volume is very large. So one is image telemetry, another is non-image telemetry. That is also small data volume, like the housekeeping data or the health of the probe. This is all low volume data. This also may come in the telemetry link. So there are 2 types of link, but as I said, it takes a long time for the signal to travel from the surface to the moon. So if you want to really operate a probe from the Earth, it may not be possible to command it in a real time. So what is done? All the algorithm for the local movement of the probe and activities of the probe, these are programmed already, and and as per that program, it moves. So it is not really commanded on real time from the Earth. Of course, the probe can be programmed from the Earth on the previous day or maybe before that. So with a low data rate connectivity itself, we can program it, or maybe the initiation of certain activities. This may be done by the command link. But the main part of the algorithm of the movement is stored in the probe itself. And this link, different types of link. For example, if we talk about Mars, there are different missions where mainly X, K, and UHF. So different types of frequencies. These S, UHF, these are on the lower frequency part. If you want a very reliable link, mostly this will be in the UHF and S band, that is the lower part of the frequency. But their data volume will be very small, not a very large volume. Whereas if we want really a high data volume, we have to move to higher frequencies like K and X band. So the different types of links and the data rates are given there in the table. Next. So these are the frequency bands, as I said, the deep space bands, S band, X band, K band, Ka band. So S band is on the lower side of the spectrum, 2.1 to 2.182 gigahertz, in that range. For uplink and downlink, there are different frequency allocation. These frequencies are all allocated by International Telecommunication Union, ITU, based on their applicability and the international coordination. So whoever goes into the moon or in the deep space, they have to abide by these rules set by ITU. And recently, we are slowly moving to optical frequencies. That means beyond KU and K, we are going to optical frequency band where we really get a huge data volume, and that has been already demonstrated by US. Okay, next. So this path loss, what we said, I discussed earlier, what I mentioned about earlier, as the distance increases, the intensity of the signal in a specific direction slowly gets reduced. That means if you say the aperture antenna and antenna of the transmitting side, the same antenna, if we put of aperture size A, if you see the last part of the diagram where 9 A's are there, it will only receive 1/9 of the signal, whatever is transmitted, because that much energy only it can capture. So as you go away from the signal, from the transmitter, the strength of the signal will reduce. And the difficulty level, if you see, from Geo, that means 36,000 kilometer to Moon, Mars, Jupiter, and Pluto, these are all in terms of 10 to the power 7, 8, 9, 10, like that. Distance is also increasing in the same way. It becomes more difficult to get a really good signal strength at those distances, far away distances. Next. But before that, signal has to go through the atmosphere. That means in 10 to 20 kilometer range on the surface of the Earth. There it is not vacuum. There we have different types of gases and cloud and rain. So this will also attenuate the signal. This will reduce the signal strength. It is not only just the distance, but the absorption due to these molecules. This also creates a fading loss into the signal and generates additional delay and dispersion. So this is how the graph is normally used for this calculating the atmospheric delay. You can say that around 22 gigahertz, there is a very high attenuation. This is the water vapor absorption band. Like that for different molecules, for oxygen, we have oxygen molecule absorption band. So at different frequencies, we have different frequency bands. So we have to select a frequency between these peaks, that is within the valleys. That part of frequency is used for any free space communication and deep space communication also. Next. So this we have discussed. So DSN basically, as I said earlier, there are 3 DSN stations of NASA. One that White Sand in US, and the other is in Australia, and the other is in Spain. And they're 34-meter and 74-meter, 70-meter antennas. They're huge antennas. They work only in the SX and Ka band. Of course, there are other antennas which are used for local communication also in the different space probes. Next. The major challenge is visibility, because as we go, say we are moving on the surface of the moon, but as you go on the other side of the moon, which is not visible from the Earth, there we cannot communicate. So there what can be done, we can have a relay satellite around the moon. So the relay satellite will receive the signal or transmit toward the Earth, and then other side will be connected with the rover or lander. So there may be frequent this non-availability of the satellite, the user probe from the surface of the Earth. So that's why if you see the Goldstone, the 3 stations of DSN, they have a wide coverage, almost covering in the entire 360 degree from the surface of the Earth. Next. Another challenge is latency. So that is the delay. Basically, it is the time when the signal starts and the time at which it is received there at the receiving port. So Mars to Earth distance, if you see, and we know the signal travels at the velocity of light. So the delay from Mars to Earth, if you see, it can take anywhere between 3 to 20 minutes. And Jupiter, to Earth maybe 35 to 50 minutes. So within this wide distance, the two-way communication, that is the interactive communication, is not possible. Normally, the transmission protocol TCP, whatever is used in the internet, in our normal internet, they always wait for the acknowledgement. That means some bits are received properly, and it is acknowledged from the receiver at the transmitting end. Once this operation is over, then only we go for the transmission of the next bits. So this is called acknowledgement. Now, in normal TCP/IP, it cannot wait for this 3 to 20 minutes, and even if we tweak it, then the data rate will become too slow. Actually, it may not be usable at all. So this is what is shown in the graph. The next. So DSN at present, they are having huge antenna and then cryo-cooled LNA, low noise amplifier. That is the first amplifier after the antenna system. So as I said, any amplifier generates noise on its own because of the electron movements. Whereas this cryo-cooled low noise amplifier, this generates a minimum quantity of noise, very, very low level of noise. So that's why they are preferred in this type of weak links. And of course, they are high power, and they have some either at the means maybe some tracking signal beacon will be there on the probe or the orbiter, which can be tracked by the DSN stations on the surface of the Earth. And space segment, if you see, there definitely we cannot put a very large antenna. So there will be a small antenna, which can be easily mounted on a satellite, small satellite or probe. So the receiving, the other side, the space segment normally is very small compared to the ground segment. And of course, they have stable oscillators which maintains the frequency and coherent carrier tracking. These are some specific requirements of the space segments. Okay, next. So this is the timeline, how the service quality is improving, and the type of services is also changing. Like initially, if you see Pioneer and Viking missions, they mostly used up to 1975. Uh, the quality of link which they are having, this is sufficient. This is sufficient to support telephony kind of signal. But beyond that, we have now fast internet and even HGTV, all high data rate signals also can be seen in the ISS and other type of space missions, and distress missions also, like Mars Reconnaissance Orbiter, like that. Next, these are all in XK and KU band link, K and optical links. Next. Now, if you see, these are already existing, whatever I have explained so far, these are existing DSN-based network. Now, if you see the future developments, there may be colonies on the surface of the Mars. So how to get a reliable link, crewed mission, particularly as for example to Phobos, it may need a data rate of 2 to 25 Mbps, and Mars to Earth, that is a data return link that may be quite high. Requirement may be as high as 100 to 200 Mbps kind of thing. So these are the requirements. So what is being planned now, that like our terrestrial internet, will have internet systems there also. So those who are going into those colonies, they can avail this communication networks. Next. So far we had the networks which used to call the delay tolerant network, the DTN. However, displace conditions, other than delay, there are several other issues like non-availability of link and simultaneously moving nodes. So there are different uh, factors which can affect the link. So slowly we are moving. So the protocols are being modified, and we are moving from delay tolerant to disruption tolerant network. So these are the new technologies which are being developed. Come to the next one. Yeah. So as I said, this type of network, reliable network, will always look for an acknowledgement. Now, when the distance is very large, it takes a long time to get the acknowledgement signal. So, what is being planned is we'll distribute the distance in a smaller period, and at each interval, we'll have a storage or relay facility. That means the smaller probes or satellites. So, from there, we can get the acknowledgement in a shorter time. And finally, over these stages, finally it will get into Mars or Moon, wherever we like. So that is the way we can get a we can call a disaster delay as well as not delay. Okay, it can tolerate the delay and disruption as well. Next, and the future definitely from RF we are moving towards optical communication. And advantage of optical communication is basically laser communication. So it is a very focused beam. The divergence, as it is called, of these beams are very narrow compared to the RF or RF links. So that's why you get a good signal to noise ratio over a large distance. And these are already implemented in some experimental cases on the surface of Moon also, demonstrated by NASA. There are direct optical link as well as indirect optical link like RF. Of course, these links will have more uh, effects due to the atmosphere and clouds and those things. The near Earth effects will be much more significant compared to RF. Next. So expanding this, NASA is planning now for LunarNet. Of course, we are also planning a similar kind of network surrounding the Moon, where we have orbiter, different elements like orbiter, lander, rover, and maybe can go to the human being also there on the Moon. Next. Yeah, and finally, as we know, we are now using all 5G, 6G services as defined by TGPP. So the similar type of services we'll get on the maybe on the surface of Moon or even Mars. So that even lander, rover, and everything can be connected with human being, and in turn they'll be connected with the terrestrial networks. Next. So this is okay. This is as I said, this will be connected with the terrestrial network. That means one person, whoever is going there, the astronaut, he can talk to somebody on the surface of the Earth also. That will be through data relay satellites. Through lunar orbiter, it will come to the data relay satellites, which are moving around the sun, and then subsequently it will come to the receiving end on the Earth. So there may be several trunk link and cross links and data relay links involved in these different types of links. Next. Okay, that is the communication part. Then we'll come to the navigation part. Navigation is basically, as you know, it is the finding, like we are using GPS nowadays for while driving car and other purposes. So basically, our positioning means finding out our exact latitude, longitude, and height from maybe minimum sea level or somewhere. So that X, Y, Z, these three coordinates we have to find out for our own self. Now, how it can be done? Historically, people have used different gadgets, and this mariners when they used to go to deep seas, uh, they used to use different kinds of compass and other navigation aids to find out the direction. That means whenever they used to cross the ocean, different oceans, how to get into the other part of the ocean. So there, the direction becomes very important, and the location also, including the time. So all these parameters earlier also people used to find out using different types of gadgets, which are not very much accurate, and there are several other issues with these gadgets. However, with the advent of with the availability of radio frequency network, next space-based navigation systems we are having now. So when you say we are using GPS or Navic signal to find out our own position, what does it mean? It means these GPS satellites or Navic satellites, if you take, there are many satellites which are orbiting around the Earth. Now, at a time, from one location on the surface of the Earth, if you can find the distance of 3 such satellites, then by the method of triangulation, you can find out your own location. That is the basic fundamental principle of navigation. Now, there is when you say that finding out your own position, that means you have to use some sort of clock. You know the velocity of light, the RF wave, that is the velocity of light, 3 into 10 to the power 8 meter per second. Now, if we can calculate the time precisely for the signal to come from the satellite to your place, if you know the time, you know the velocity, then you can find out the distance from each of the satellites, your distance from 3 satellites. And if you plot a sphere surrounding each satellite with the same radius, then they will convert at one point or maybe 2 points. From those things, you can select your own point based on the feasibility. That means you are, if suppose are away from the Earth, so definitely you can eliminate that point and you can take the point which is on the surface of the Earth. But the issue here is to calculate the time, and your clock may not be synchronized with the clock of the satellite. So if there is any difference, that will introduce an error into your calculation. That is when you are finding the distance, the range, what it is called. So to eliminate this difference, you need basically through number of equations, you can show that if we have another satellite, that means if we can track my distance, if you can range my distance from 4 satellites, of course, the location of the satellites at that time should be known precisely. Then you can find out your position in a very, very precise way. So that is the fundamental principle of uh, GPS or positioning system, whether it is GPS or NAVI. So basically, we need 4 satellites, and in that case, your clock need not be perfectly synchronized with the satellite clocks. You are allowing for some dispersion. So you can find out your X, Y, Z as well as the precise time, with 4 equations. Next. So these RF navigation systems, it has started with, of course, there are different mechanism of this RF navigation systems also. Some are Doppler based, some are based on this triangulation. So the LoRaWAN, Transit, Omega, and GNSS. GNSS is the latest system, that is GPS and Navi. These all fall under GNSS system. So they can give very precise, as the GPS claim, it is around 20 meter whatever position accuracy, which you can derive from the signals, GPS signals. So with the signal itself, each satellite, they transmit their own location precisely. So you know the time and you know the position of the satellite, so you can find out your own position using 4 equations. Next. Now, how can you use this GNSS into the deep space? That is the question now, because this GNSS systems are basically meant for the terrestrial system. That means the signals is transmitted towards Earth. Now, as you see, these are GPS system is all in MEO orbit, and our NAVIC is in GEO and GSO orbit. Now, if you see this antenna pattern through which the signal is transmitted, they have a main lobe and some side lobes also. That is the natural behavior of antenna, any antenna. So what happens beyond the surface of the Earth? It is the signal which is transmitted through these side lobes. This can be received from a far away distance. which will not be obstructed by Earth. The main lobe gets obstructed, but the side lobe remains as it is. So you can get a moderate strength of signal from outer space, from maybe from the cislunar interval also, or maybe even in the surface of the moon. Of course, you need a very, very sensitive receiver in this case, because you are going far away from the Earth, and the GPS system is not meant for that kind of distance. But as an opportunity signal, you can get this GNSS signals there and find out your location with respect to Earth, which may be finally transferred into a lunar reference or plane also, orbital system also. Yeah, next. Yeah, this is how this cislunar distance, the distance between the Earth and the Moon, there the signal travels, and in between you get the shadow, Earth's shadow. But the signal is 30 times weaker than they are on the surface of the Earth. Of course, one more issue that matters is this dilution of precision. We call it DOP. That means how these four satellites are distributed. The satellites which are transmitting the navigation signal. It depends on the specific geometry. If they are all are from the same side, it gives a very bad DOP, which is not good for your position determination. Unfortunately, when you see from the moon, these all satellites will come in one side only. So it is not good for position determination. However, in a course things up to the course level, you can find out in, your location also in this place. Next. So there are three types of systems which are being planned for lunar PNT now. That is the position and timing services on the moon. One is, as I said, using the GNSS signal. Then we can have a small satellite constellation. And there is another type of system that is called relative positioning system. They consist of pseudolites. Pseudolites means basically they work like a smaller satellites, but they are smaller terminals which transmit their own location. But this works in a very means a limited area. For a limited area, you can get the location service. So over the surface of the moon, if you can place the pseudolites, the small terminals, navigation pseudolites, at a specific known points, then they can provide a very good local positioning service. Of course, it will not be absolute at an absolute level. Then there is another approach which combines this small satellite constellation like GNSS around the moon plus the pseudolite. If you can combine these two things, then you can get a very good accuracy, but over a smaller region, maybe up to 10 kilometers. But the accuracy you can get maybe up to sub-meter level also. Next. So this is how the timing information, the most important thing, this network has also to be synchronized with the GPS or any centered systems. So basically the timing information you have to pass correctly from the terrestrial network to the lunar network. So this is of very important, very much important to transmit the timing information properly into the other network. Next. Of course, there are other absolute position determination systems which are called pulsar navigation. Basically, there are some X-ray pulsars. Pulsars means they are very distant stars, which dead stars, which emit X-ray signals in a pulsed manner. And they have slightly different frequencies, though they are all X-rays only, but their frequencies are slightly different. So we can differentiate the signal coming from one pulsar to the other. And using this number of pulsars, 3 to 4 pulsars, and we have ground-based observations also. So along with that, we can create a very good system which can give a a very good position accuracy in the deep space. So there are other methods like delta DOR, which all depends on this kind of systems. Next. So I think we have come to the end of the talk.